This is just a plain old stick. And what can you do with a plain old stick like this? Well, you can do geometry with it. You can measure the height of your house, or a building, or a mountain. With a stick like this, a great mathematician, Thales of Miletus, in 585 BC, measured the height of the Great Pyramid of Cheops. And another great mathematician, in 280 BC, used a stick like this to measure the size of the Earth. You can use a stick like this to find the direction of north, south. You can measure your latitude and longitude. You can determine the time of the day and the day of the year. You can use this stick to measure, calculate, compute. This stick is a computer. This stick is the great-great-grandfather of this modern computer here, and it has taken 3,000 years of mathematics to separate these two computers. Ancient Egypt is the cradle of mathematics. Even before 4000 BC, the Egyptians had considerable knowledge about mathematics. They had already fixed the year as 365 days by counting the number of days which intervened between two successive occasions when Sirius, the brightest star in the heavens, was just visible over the horizon immediately before sunrise. Here we see the horizon due east as the Egyptians would have seen it in 4000 BC. Sirius appears over the horizon and almost immediately the sun rises, its blazing light blotting out the stars. This is called the heliacal rising of Sirius. Such proximity of the sun and Sirius only happens once a year. By the next day, Sirius rises about 4 minutes earlier than the sun, and earlier still the following day, with the angle between them increasing, until 365 days later, the same spectacle is repeated. To the Egyptians, the heliacal rising of Sirius was the first day of the year in their calendar. This day was celebrated with festive rites and rituals. It was generally around this time that the flooding of the sacred river Nile began, bringing prosperity to farmers and cultivators along its fertile banks. They saw the sun as divine light and fire moving around the earth against the background of stars, repeating its motion exactly every 365 days. They counted with pebbles by associating each day with one pebble, a one-to-one association. It took 365 pebbles from one heliacal rising of Sirius to the next. They also observed that the position of the rising sun on the horizon changes every day until it reaches the extreme position south of east, then it stops, a solstice, and moves back until it reaches the extreme position again north of east, another solstice, and then it moves back again, repeating the same movement. Some early Egyptian monuments suggest that the day of the equinox was fixed in the following way. Two poles, A and B, were placed in alignment with the rising sun of the summer solstice, and another pole, C, was placed in alignment with the rising sun of the winter solstice. The distance between A and B was made the same as the distance between A and C. Midway between these two extremes, the sun rises due east exactly, and on these 2 days, the lengths of the day and night are equal. Hence they are called equinoxes, from equal and night. Such days were of great importance in the ancient rituals. Notice that the point exactly due east on the horizon can be obtained by bisecting the angle BAC. So you can see that a lot of information comes from the position of the sun on the horizon throughout the year. The Egyptians also observed the position and the length of the noon shadow from an obelisk and found that it changed every day. They marked the tip of the noon shadow every day and discovered that it produced a curve, like a figure of 8, but with unequal loops. It is called an analemma. This curve was used as a calendar, with pebbles as markers for each day of the year. It reveals a lot of information. The day on which the length of the noon shadow was the shortest corresponded to the summer solstice, and the day on which the noon shadow was the longest corresponded to the winter solstice. Today we understand that the shape of this curve is a result of the tilted rotation of the Earth's orbit about the Sun. A simple experiment will verify this. If you take a camera and mount it so that it takes a wide-angle shot of the Sun every day and at exactly the same time onto the same negative, you will find, on developing the film 1 year later, that the position of the Sun changes every day and produces the analemma curve in the skies. The ancient tradition of using the analemma as a calendar and a timepiece can be seen today in the construction of analemmatic sundials. The central part of these sundials is the analemma curve calculated for the observer's latitude. It has a series of fixed hour points which are located around the circumference of an ellipse. By adjusting a vertical gnomon along the analemma to a point corresponding to a particular time of the year, the shadow falls on the ellipse displaying the local time. This unique analemmatic sundial is located in the beautiful Mount Annan Botanic Gardens in New South Wales. It is the only one of its kind in the world and was designed and built by Dr. Margaret Folkard and John Ward from Adelaide. It is appropriately called the sundial of human involvement because any person standing on the analemma acts as a gnomon, throwing a shadow onto these splendid basalt columns used as the hour markers. It tells the local time accurate to the nearest minute.